Okay, so a warm welcome to everyone, a few who is there right now. It's a pleasure today that we have Dr. Haixu Wu, who is a postdoctoral researcher in the Computational Design and Fabrication Group at MIT CSAIL, working under the supervision of Professor Wojtek Matusik. So just to give you a little bit of background, he did his PhD and bachelor's degree in software engineering from the Tsinghua University School of Software, where he earned also a second degree in pure and applied mathematics. His research sits in the intersection of deep learning and scientific machine learning with a particular focus on sequence modeling, physical world modeling, and PD solving. His work has already made significant impact across multiple domains. Some of his works, for example, his PD foundation model Unisolver recently won a third place in the Fair Universe competition at NeurIPS 2025. His unified forecasting model, Core-Former, was published as a cover article in Nature Machine Intelligence and received Youth Outstanding Paper nomination at WAIC 2024. So there are many like these to his name. He has also been recognized with numerous prestigious awards, including being named a Byte Dance Scholar, receiving the National Scholarship twice, Xinghua's Top Grade Scholarship, and many others. So today we are going to be not wasting any more time, and we'll try to listen from him his interesting work on Transolver to Transolver-3. And with that, please join us in welcoming Dr. Haixu Wu. Over to you.
Yeah, I think everyone can hear me. Okay, hello. Thanks for the great introduction and the invitation from Samdata. I think it's very exciting for me to give a talk in such a scenario, especially have a lot of experts from physics and numerical methods and mechanical engineering. I think it's because PD solving is quite joining interdiscipline, so I think it's really valuable to receive some feedback from other domains. Okay, we can start. My name is Haixu Wu. I graduated from Tsinghua University and currently a postdoc at MIT CSAIL. Today, I'm going to talk about some progress on neural PD solvers, and the talk title will be From Transolver to Transolver-3, Scaling Neural Solvers to Industrial Scale Geometries. And because my previous research field is machine learning and computer science instead of physics, so this talk may provide some perspectives from the machine learning researchers. Hope it can be interesting to you. Okay, I would like to start with some background. In the real world, there are very interesting phenomena like turbulence or atmosphere circulation and stress. A long-standing and fundamental question is how to understand the world. And because I'm from the machine learning community, a widely used and well-established approach is data-driven, which usually starts from the intuition or vision. It means we can record this process as an image or videos using a camera or other types of sensors. After that, we can learn a vision model to approximate these dynamics. And the above-mentioned approach works in some tasks, which is also named as world model by some researchers, I think. However, current video models still struggle in modeling the physics process very accurately. Sometimes the generated results are not very physically reliable. And if we think about this phenomenon from a more basic view, we will find that these phenomena are inherently governed by scientific rules. Specifically, extensive physics process in the real world can be precisely described as partial differential equations, short as PDEs, such as the Navier-Stokes equation shown here. This is for fluid dynamics, and the stress-strain relation in solid mechanics shown here. Accurately solving these PDEs are very important in understanding the world and the supporting engineering, such as weather forecasting and industrial manufacturing. However, solving PDEs is a great challenge actually, and clay mathematical institution list this problem of Navier-Stokes existence and smoothness as the 7 millennial price problems, which is in parallel with the PMP problem in computer science. So it's really hard and usually impossible to obtain the analytic solution of PDEs. Fortunately, after decades of efforts, we have very mature numerical methods, such as FEM or spectral methods. And these methods can solve PDEs very stable, but suffer from the huge computation cost. I mean, if you want to simulate a car, it may take hours or even days. And if you want to simulate some high-speed fluid, it will take more time. And recently, some neural PD solvers have been explored, which are based on a pure data-driven paradigm. And the researchers attempt to utilize the learning capability of neural networks to build an efficient surrogate tool. Once the model has been trained based on the PD data, it can make the inference within several seconds. So it's very efficient during the inference stage. And the neural PD solvers has been already used in some simulation softwares, such as the SimAI, software in ANSYS. The working flow is like you pre-train a model to simulate the car. And after that, you can directly apply the model to a design process to get the immediate feedback. In this way, you can speed up the industrial design. And there is another software named as Physics AI in Autel. In this software, they support to directly applying the PD solver to CAD programs. I mean CAD geometries, like the input is not the computation mesh, but the continuous sphere. So it can directly apply to the design process. And these are two introduction videos to present how this type of software works. There are a lot of industrial softwares can enable AI-powered capability. So I think this is a very valuable direction. And neural PD solvers is not only a hot direction in the physics community, but also a booming direction in the ML community. I think it's about 2 years ago, since 2024, every mainstream ML conference will hold special workshops or tutorials to discuss the topic. And I can still remember the AI for DE workshop in ICLR 2024. The meeting room is so crowded, so I couldn't even enter the activity. So I think this is a very hot topic in ML community. And if we count the number by searching their titles with keywords, we surprisingly find that the papers about PDE or physics are comparable to the world model if we only consider the accepted papers. World model is a really hot topic in current AI and ML communities. And additionally, I think PD solving is still an unsolved problem. You may have seen some demonstrative videos from Google Genie in recent days because it's really popular. The latter case is released by Google. You can see the Google Genie can simulate very complex fluid dynamics in the realistic work. I think the performance is quite impressive. And the right one is a test case from Twitter, which is we can find this model, although it's good at realistic work, but it's still struggling to generate the physically reliable dynamics. If we focus on some expert domains like industrial design, it's not very perfect. And during the past 2 years, my PhD lab and I have focused on this challenging problem. And we have attempted to build practical neural PD solvers, which can support complex geometries, high-fidelity simulation, as well as the diverse simulation scenarios in industrial design. Due to the time limit in this talk, I will only focus on the first two parts, how to solve the complex geometries and large-scale meshes. And I will present our exploration in Transolver, Transolver++, and Transolver-3. Okay, the first one is Transolver, which is a fast transformer solver for PDEs on general geometries. I would like to start from an industrial design problem, like you want to design a car. You need to estimate the drag coefficient of every design. It will require the model to predict the surrounding wind and the surface pressure, which is quite difficult because it involves a lot of difficulties for neural network at that time. First, it needs to handle large-scale geometries, which will bring a huge computation cost. And secondly, it involves very complex and unstructured geometries. So you will need a good geometry representation. Third, the governing equation will drive intricate physics correlations, like because it's driven by Navier-Stokes, and this equation is quite complex under different scenarios. Although there are some prior explorations on GN, like GNO or other things, and some exploration based on Fourier basis, their performance is actually not very satisfactory in such tasks. And in this work, we want to explore the transformer-based PDE solvers. And the transformer can be viewed as a foundation of modern deep learning. So I think if we can introduce such advanced backbone into PDE solving community, it will unlock a lot of deep learning advanced techniques in this community. So I think this is very exciting. And under the PDE solving context, basically we can flatten the computation mesh into a point cloud sequence, and we can adopt the attention mechanism to calculate the physics correlation among different mesh points. And this can be formalized as a process to approximate a Monte Carlo-based integral. So it has some theoretical foundations. And here is the proof of how to formalize the attention mechanism as a global integral. Basically, you can do two things to achieve that. The first is to view the computation mesh as a sampling of the continuous domain like this. And the second is to view the dot product attention as a kernel function. So in this way, you can reformalize the attention calculation into a global integral. But I think this formalization is quite elegant because we can have a very fundamental understanding about attention mechanism. And despite there is a good theoretical understanding and expressive capability in Transolver, in Transformer, directly applying the Transformer for PDE solving still suffer from two drawbacks. I think the first one is quite obvious because attention mechanism is of a quadratic complexity with respect to the sequence length. So it means you can only process meshes within a certain number of points, otherwise you will suffer from the out-of-memory problem. And secondly, it's really hard to capture the physics correlations among massive mesh points. The attention learning will be overwhelmed. But we think how to efficiently capture the physics correlations underlying the discretized meshes is actually the transformers into practical PDE solvers. So I think this is the key insight when we're designing Transolver, Transolver++, and Transolver-3. And based on this idea, we want to present Transolver based on a very fundamental idea. As we discussed it before, because the computation mesh can be viewed as a sampling of the continuous domain. And the previous works basically trapped it to this sampling meshes. So I think their modeling is from a very superficial or unwieldy viewpoint. So I think they will suffer from many difficulties in computation complexity, geometry modeling, and physics learning. And in Transolver, we attempt to learn the underlying physical states, which I think is very intrinsic, and it can naturally bring better efficiency geometry learning and physics modeling. So this is the basic idea of Transolver. We want to get rid of the unwieldy computation meshes and focus more on the continuous domain. And when I'm talking about the physics states, I mean the internally consistent clusters. Like here is a visualization of Transolver learned physical states in different PDE solving tasks. For example, in car simulation, the model learns to ascribe all the front surface, like here, to a token, to a physical state, I mean. The highlighted region means the related points in a certain physical state, and the real parts of the car is in another state. And we name this learning process of physical states as slides. Because it's intuitively like we slice the physics domain into several subparts. And after that, the physics states are further encoded to several tokens. And we name that as physics-aware tokens. I know if you are familiar with computer vision, you may find that the basic idea is quite similar to the petrify operation in vision transformers. And the difference is that Transolver focuses on the irregular geometries, and the slice operation is not like the predefined petrify, but is a learnable parameter. Okay, here is the overview of Transolver. It applies attention to the learned physics-aware tokens here. And we name the key operation as physics attention. The whole process is actually a newly defined attention mechanism. And the process can be split into three parts. The first is from mesh to physics tokens. This is conducted by slice operation and apply attention to the slice tokens to approximate the global integral. And after that, we can project the transformed physics tokens back to the mesh domain where the deslice operation. Here is the slice and here is the deslice. Here is the attention among tokens. Okay, for the first step, we attempt to project the mesh point representation from the mesh domain to the physics-aware tokens. To achieve this, Transolver is designed from a bottom-up view. Firstly, we assume there are m potential physics states inside this task. And then for each mesh point, we apply a softmax-based classification with m categories. And after that, we can obtain the possibility of each mesh point belonging to a certain physical state. And the softmax operation can ensure a low entropy slice, which can avoid the learning process degenerate to a global pooling. It's a very obvious because, for example, if X has the same possibility to be ascribed to every possible physical state, so the whole design will be degenerated to every pooling. So this is very bad because we want to learn some informative physical states for the class to split the whole continuous domain. So we use the softmax-based design to ensure a low entropy process. And after that, we actually obtain the spatial distribution of different physics-aware tokens like this. This is for token 1, this is for token 2. Then we aggregate the point-wise mesh representations based on the learned slice weights. And this is like a global weighted sum for different tokens. This can project the n mesh points into m slices. And it's worth noticing that the aggregation is not random or average pooling. It will ensure the information of each physics-aware token internally consistent because we only aggregated the mesh points from the same token. So this can ensure a very compact and informative compression for the whole continuous domain. Next, I can adopt the attention to these tokens because these tokens are internally consistent and is very informative, which can also be viewed as a global integral in the physics domain. Actually, the attention part is just as a canonical one. It is based on the dot product similarity like this. However, the token here is our newly learned physics-aware tokens instead of the mesh points. It can reduce the sequence length from n to m. It can benefit the efficiency. And in Transolver, it also captures the interactions among different states instead of the massive mesh points. So I think the representation learning and the physics learning process are more robust. And also it can prove that the attention in the physics domain is also a learnable integral operator. I will talk about this later. Okay, after attention, the interacted physical states are projected back to the mesh space because we want to get the physics quantities in the mesh space. This is finished by reusing the slice base like this. It's quite interesting because during the slide, our slice base is in the shape of n by m, and during the deslice, we are basically doing something like from m slices to n mesh points. That's why we can use the slice base in this slice process. And we also provide a theoretical understanding of Transolver. Previously, researchers have proven that attention is essentially a learnable integral in the mesh space. However, in Transolver, the attention is applied to the projected physics domain. So is physics attention still input domainable? So I think the answer is yes, and we have proved that based on these derivations. And during the proof, we can derive all the components in physics attention, like slice, d-slice, and attention among slice tokens. So I think this also provides a theoretical justification for Transolver design. Okay, this is the technical part of Transolver. In this paper, we conducted extensive experiments to examine the performance, including 6 standard benchmarks and 2 practical design tasks with more than 20 baselines. And the result in our paper is quite impressive. Firstly, Transolver can achieve about 22 error reduction over the second best model in 2024. This is tested on the standard PDE solving benchmarks proposed by Zongyi Li. And besides, Transolver is also excels at design tasks. Here we adopt Transolver to predict the surface and surrounding physics quantities of the driving car and flying airfoils. Transolver can accurately predict the physics field with complex geometries like the connection part of the windshield and engine hood. And also we calculate the drag coefficient and lift coefficient from model predicted physics fields. The R square for these physics quantities is over 99%. So it's quite practical if you use this model in benchmarking different designs. Here is an efficiency comparison under different size of input meshes. The pink curve like this is Transolver. Sometimes Transolver is even faster than linear transformers if you want to process some large-scale geometries, because the slides can be viewed as a tokenization. It can bring a further constant scale speed up. Here is the visualizations of physical states. You can find that learned physical states are quite diverse like that they capture different patterns inside the physics process. And this can verify the express capability of physics attention. And besides, because we are using a transformer backbone, Transolver demonstrates very favorable scalability. We test the 3 things. The first is model performance with respect to the input resolution. And second is the model performance and the different data size. And then we keep increasing the model parameter to see what's the performance change. Okay, we can find that the Transolver can achieve a very stable performance under various input resolutions and keep benefiting from ending data and ending parameters. It means Transolver is a very scalable backbone. It has a great potential to be extended to a physics foundation model. I think that is very promising. Okay, besides, we also test the Transolver under some out of domain scenarios like unseen real number and unseen angle of attack for simulating the flying airfoil. Under this setting, Transolver still performs the best Spearman correlation, which is around 99%. This is quite interesting because in different real number and different angle of attack, the physics scenario will be quite different. So I think this OOD generalization is quite hard. And because Transolver is mesh-free, it can also be used in Lagrangian settings like modeling the particle dynamics. Compared to the previous GN baselines, Transolver can better capture the splanting for the dropping water. I think this may be benefited from the global modeling capability of Transolver because it can better capture the large-scale interactions inside the fluid. And our code has been open sourced. Transolver has also been integrated to the NVIDIA Physics NeMo. This is a scientific machine learning framework open sourced by NVIDIA. By the way, I also want to thank the Physics NeMo team who keep optimizing Transolver in training techniques and recognize our performance in high-quality CFD simulation. They also test Transolver in industrial crash tasks. This is very surprising because this task contains very complex fractures and nonlinear deformations, and Transolver can also be applied to such complex tasks. Okay, that's about the Transolver part. This is the first paper we published in this Transolver family. So although the performance is quite impressive in vanilla Transolver, it actually has some, I think it's kind of magic design. For example, in the slice operation, like in this process, why we adopt the global weighted sum to generate the physics-aware tokens. I mean, obviously, you can do something like cross-attention, so why divided sum them? And besides, during the deslice operation, why we reuse the previous learned slice weights for the deslice? You can newly learn a weight tensor for the deslice or adopt the cross-attention. And actually, previously, some researchers has reached out to me to discuss these two designs. And honestly speaking, I do not know the answer when I initially designed the Transolver. I just adopt this design because they are simple and parameter efficient. But lately, I find that it turns out these two magical designs are actually the unique feature of Transolver, which can be fully utilized in Transolver++ and Transolver-3 to support the scaling up the geometry to billion scale. It's quite surprising to me. Next, I will talk more about how these two unique designs can be used in supporting Transolver++ and Transolver-3. Okay, the next is Transolver++. In this paper, we built an accurate neural solver for PDEs on million scale geometries. Here is an intuitive case. The left benchmark is tested in Transolver. It only contains around 30,000 match points. And the red one is a task we want to solve in Transolver++, which contains millions of match points in each case. Notably, the right one is actually what we want to do in the industrial practice. So I think this process is quite significant. And concretely, the geometry of Transolver++ is about, I think, 100 times larger than the previous benchmarks. And we have do our best to fit the largest PD solving task in Transolver++. Specifically, if we benchmark the upper bound of geometry size in one single A100 GPU, it's like the upper bound of Transolver is 0.6 million in Transolver and 0.3 million in GNOT. None of the previous work can handle million scale geometries in one single GPU, and Transolver++ is the first one to achieve that. Actually, the large-scale geometries will bring many new challenges to the PD solving. This is quite intuitive because if you can cut the problem as a sequence modeling task, like the large language models, basically making a large language model able to handle millions of tokens is not only a scientific problem, but a very challenging engineering task. Currently, researchers and engineers has made a great effort to speed up the AI infrastructure. Therefore, we also want to solve the challenge of scaling up geometries by building a domain-aware analysis. Actually, we are doing something like a system design. Okay, let's recap the design in Transolver. We have 3 steps: from mesh to physics, physics attention, and from physics to mesh. And if you apply Transolver to large-scale geometries, we find that it may suffer from 2 main challenges. The first is homogeneous physical state. And here is the physical states if we apply Transolver to DriverNet++, which contains million-scale geometries. And you can find that the learned physical states are quite similar to each other in the last layer. This is quite intuitive to understand because you are basically trying to identify the similar match points from a very massive candidate set. So it's really hard to pick the similar ones from a very large scale candidate. And in Transolver++, actually, we improve the physics learning process to enable a very informative physics learning to guarantee informative physical states. And secondly is the efficiency bottleneck. For million-scale geometry, even an intermediate representation will consume about 2 GB of the GPU memory. So if we consider a A100 GPU with 40 GB memory, which can only take about 20 representations. So it's a very strict constraint for architecture design. And in Transolver++, we made 2 upgrades. The first is upgrading physics-based learning with eidetic slices. And specifically, we adopt an adaptive temperature for the slice operation. So what's the benefits of adaptive temperature? Let's take the car simulation as an example. Actually, the physics interaction of the car roof is quite simple. So ideally, Transolver needs to assign the roof mesh into one certain physical state with high confidence. However, if we visualize the slice weight distribution here, the blue curve is Transolver, and we can find that the vanilla Transolver still does not have a very confirmed assignment for the roof part. Built with adaptive temperature, Transolver++ can learn a very distinguishable distribution like this, like the red curve, with special concentration on one certain physical state. So this can avoid the degeneration of physical states. The second design made by Transolver++ is that we notice that slice design, the slice process is natively parallel, and this allows us to design a parallelism framework for Transolver. So the whole pipeline is like this. Firstly, we split the large mesh into several subsets, and we assign each subset into a certain GPU. Next, we calculate the physical states independently on different GPUs based on a subset of mesh. Then we can async the calculated physical states among GPUs. The special global sum design I mentioned before empowers Transolver with additivity. So if you directly add the physical states calculated from the subsets, it's equivalent to calculate the physical states from the entire mesh. Therefore, with a little communication overload among GPUs to async physical states, we can obtain an equivalent result with respect to the whole mesh forward. And because we only async the physical states, which is around a quarter of a megabyte. So the parallelism framework is very efficient, which is much faster than deep speed and ring attention in the scaling capability. Besides, we further calibrate the code of Transolver and reduce the redundant intermediate representations for further speed up. And this is about the technical part of Transolver++, where we upgraded the physical state learning and utilize native parallelism framework of Transolver. And with Transolver++, we finally support the industrial applications, like the showcase here in DriverNet++. Our model achieves over 20% error reduction compared to the other models. And in aircraft design, Transolver++ is also better in a high-speed simulation task, which achieves lower error in the sharp edges like this. Okay, that's about the Transolver++ with scaling up the geometry by a parallelism framework. And at last, I want to talk about our recent work, Transolver-3. Actually, in this paper, we just finished this project a few days ago, and the preprint paper will be released in this week. In this paper, we actually want to go back to the original design of Transolver and demonstrate that with the special training and inference strategy, Transolver is still the state-of-the-art in the latest high-fidelity benchmarks, although it has been published about 2 years. The title is Scaling Up Transformer Solvers to Industrial Scale Geometries. And in this paper, we actually focus on over 100 million cells geometries, which is over 10 times larger than the benchmark of Transolver++ and over 1,000 times larger than the vanilla Transolver benchmark. This is a very exciting problem because even the extremely optimized AI infrastructure for large language models cannot support over 100 million tokens in one inference. And we can achieve this in Transolver-3. Firstly, we made a detailed complexity analysis here. We can find that even in physics attention, this is a very efficient attention mechanism. There are still some under-optimized operations in slice and deslice. Specifically, the mesh size in this task, the mesh size n is much larger than the number of channels C and the number of physical states M. Thus, we need to pay attention to the big ON operations like here, here, and here, which are only in slides and these slides. And if we dive into the computation of slides parts and these slides parts, we have a very interesting finding that these operations has a very large intermediate representation like here. This is with shape n, n times c. And the additional memory cost is actually because our writing habit in PyTorch code. And because in practice, you will use PyTorch for the implementation, and you will leave some intermediate representations. I think because this is a writing habit, I want to write the code for a more clear format. So in this way, I will leave some intermediate representation, but these are not necessary in the computation. And we can remove this large intermediate representation by changing the association of metric multiplication. Like this, for example, in slides of Transolver, it's basically doing some multiplication like this. And with this, you will have a very large intermediate representation as a result of this two multiplication. And then you can change the association order from this to this. In this way, you can remove the large intermediate representation to save memory and time capacity. And with this design, we can successfully remove the big ON operation. And similarly, in these slides, we can do the same thing to remove another big ON operation in this slides process. So based on the slides and these slides in the optimized version, we further build a new training strategy for Transolver-3. Because in this paper, we want to handle the hundreds of million scale geometries. It's quite large. You cannot load all the geometry into GPU simultaneously. So we propose a amortized training strategy. Outside the model, we randomly sample subsets from the huge mesh at every iteration. This is actually an amortization design. We basically doing the amortization to amortize the training overload into multiple iterations. And inside the model, we adopt the gradient checkpointing technique to avoid storing the intermediate activation tensors, and use inside sequence computing to reduce the peaky memory usage. And the inside design is training computation for memory. Basically, you can view this operation like we want to encode the Transolver parallelism framework inside the model, not based on multi GPUs. And during the inference, we also propose a new strategy. Note that in the previous amortization design, we basically separated the PDE solving process into several subsets, and it can reduce the memory, but cannot get the correct physical state because the right state should be inferred from the entire mesh, not from the subsets. Fortunately, because we have the additivity of physical states, then we can accumulate the physical states among different subsets. Then we can obtain a correct physical states, which is almost equivalent to the direct inference based on the entire mesh. Then we can catch them for the later inference. Based on the catched physical states, which aggregate information from the entire mesh, the special design of reusing slide weights for these slides in Transolver supports the inference at the arbitrary position, which is just like the pin style. Specifically, if we only input one point, we can adopt the trained slide weights to generate the slide weights for this point. And then we do not need to calculate the physical state again, just adopt the cached state, which are correct and more efficient. And the final output of each layer is decoded based on the cached physical states and the newly generated slide weights. So in this way, Transolver-3 can support arbitrary position information, enabling inference on over hundreds of millions mesh points. So this is the way how we're scaling up the geometry. We're basically doing something like amortize the training and accumulate the physical states from different subsets, and use this cached physical states as well as the point-wise inference capability of Transolver to support arbitrary position inference. And if we do this in parallel, we can handle very large geometries. Okay, let's recap the previous mentioned magic design in Transolver. Actually, each reader design turns out to be a necessary feature for scaling up and arbitrary inference. So I think this is quite impressive for me at least. As for Transolver-3, we test its efficiency. It can process around 3 million points in one single GPU, which is 5 times larger than the vanilla Transolver. And I think the blue curve is vanilla Transolver. Sorry, the green curve. And it's about 2 times larger than the Transolver++. Along with the amortization training, it can support industrial scale applications. And in this work, we have made an exhaustive optimization for the physics attention. I think we have done our best to accelerate the calculation of physics attention. Although it cannot reduce the G-flops significantly, but in practice, it will give a 3 times speed up for the inference latency, which is quite impressive. And here we test Transolver-3 in the largest PD solving benchmarks, including the NASA CRM, Ahmed ML, and Driver ML. The largest one contains about 160 million cells per sample. And in total, it will have 31 terabyte data set for the training and the inference. The result is very exciting. Without any architectural design, only upgrades the training and inference paradigm, Transolver still achieves the best performance. Here are some showcases. You can find the Transolver present lower error in the complex geometries, like here and here. And we can find the Transolver-3 can better predict the wake flow, like the splitting flow in here and here. Well, in other models, the prediction is not satisfactory. And if you look back to the journey from Transolver to Transolver-3, the process, the geometry size has been largely improved. So why we pursue the geometry scaling? I think the answer is we are actually pursuing the ultimate accuracy. Just as I mentioned before, the computation mesh is just a sampling of the continuous domain. So if we can process the large geometry, we can ensure a more accurate approximation of the physics field, as demonstrated by the geometry scaling curve shown here. With large geometries, we can have better accuracy. Okay, by the way, I want to mention open source library named as Neurosolver library. And we built this library with many built-in advanced algorithms and datasets. So if you are interested, you can scan the QR code and try Neurosolvers. Okay, last I want to thank my advisors, Professor Long, Professor Matusik, and Professor Wang, as well as my collaborators. That's all. Thank you.
Thank you so much, Haixu. I can open the floor for questions. I'm quite sure there are a couple of questions from the audience.
Okay, any questions?
Yeah, maybe I can go. Yeah, Sonata, if you have any question, you can go ahead. Else I'll actually.
I wanted to ask about the amount of data, but I can go at the end. Go ahead, Rasdeep.
Okay. Yeah, it's a very nice talk. So I had just 2 questions. I'll keep to only 2, just letting others to also speak up. So you have shown some examples, very good examples. And I was thinking, like, did you actually enforce any physics while you're doing this? So I understand the architecture, but do you enforce a physics? For example, if you're doing this driver ML, or there's also CFD physics, like Navier-Stokes equation. Are you enforcing those as constraints?
Okay. I think in the Neurosolver paradigm I'm working on, most of these models only based on the scientific data. We do not directly or explicitly enforce the physics constraint like pings. We just learn the model from some physically reliable data and make the model can generate the data following the physics reliable manifold. So I think that is the point. We do not directly enforce the equations into the solving process. But I think it can be more accurate if you can introduce physics-informed loss as a loss function, additional loss function to the solving process. And there are some physics-informed neural operators works trying to infer that. I think that is promising.
Okay, great. Thanks. The second question is about, so what I understand is these physics-aware tokens that you talk about is basically like you have these mesh points and you convert, instead of taking each mesh point as a token, you're taking a kind of, yeah, these like, for example, if I see this example, this was a very useful example for my intuition. So like you have the bonnet of the car and that becomes one particular token, right? So
Yeah, we projected the surface into multiple tokens. It's like you do the clustering on the point-wise representations. You have different clusters, and each cluster is projected to one token. Yeah.
Okay. So yeah, from that perspective, I was thinking like, is it necessary to actually mesh the entire thing and then get the tokens, or can you also do same directly on the CAD geometry?
Actually,
So
okay.
yeah, I was just
Let
thinking
me
because
think
you're
about this
showing these
question.
images of cars, and I was thinking like you could also get these images, let's say as a CAD model, and then you probably would not need to mesh it first and then do it, but directly. I mean, I'm just trying to understand, yeah, if it could be
Yeah,
possible.
this is a very interesting topic, actually. I think you are posing a very promising direction for Transolver upgrade. Recently, I also do some research about CAD programs because they're basically representing the geometry with boundary representations, like you recorded several control points and the weights of control points. So I think if we can encode these control points, just input the information of the control points and do the slice operation, you can also get some aggregated slice tokens like here. But the input domain will be kind of different because the control points is a more mathematical representation. They are not directly related to the geometries. So I think the first thing maybe do some pre-training to align the CAD representation and the shape representation. Yeah, maybe this is a possible way to ensure that. But I'm not sure. Maybe you directly apply Transolver to CAD programs that works. I don't know. But I think this is a good point for Transolver 4 if you want to working for that.
Thank you so much. Yeah, thank you.
Thank you.
Thank you, Rasdeep. We have a lot of interest from the audience. Zhizheng, you can go first.
Okay, hello, Haixu.
Hello, hello.
Hello. It's a very excellent topic. I'm very interested in that. About last week, I have a presentation also in this topic. I used the transformer with a physical inform, and the result is very good. So I want to ask a question about how do you think about the Fourier neural operator, deep net, and the transformer-based neural operator? So these three, I think, operator learning way are the most important way. So how do you think about their future? Do you think the transformer will be the most important operator learning in the future?
I think this is a tricky question. I think in general, I think the community needs more diverse designs for different architectures because without these explorations, we cannot get the right way. And it's really hard to say Transolver is the rightest way to operator learning. I cannot say that, but because from my mindset, and from the machine learning community, so I think if you want to pursue a right way for operator learning, or at least for deep learning, you should pursue a scalable architecture. That is my method, but I don't think it is shareable. It is shared with many other and with other researchers from different domains. Why I choose transformer as the main architecture, because I think transformer is a very established backbone in many domains, and it's scalable. So that's why I choose transformer. And it's also possible to make DeepNet or FNO as a scalable architecture like AFNO. say, try to integrate FNO with transformer architecture. So I think that is a very promising exploration. So I think that is the answer. The answer is, if you want to, from the machine learning community, my method is, if you want to pursue the ultimate architecture for the future, you need to focus on the scalability. Yeah.
Okay, thank you. Thank you for your answer. It's nice to talk with you. Thank you.
Thank you. Thank you.
Thank you, Zhizheng. Wei, you can go next.
It's really a nice talk. And I have two questions. The first one is that both for your Transolver++ and Transolver-3, you do two different types of modification from the Transolver. Like Transolver++, you use the temperature adaptive, and for the Transolver-3, you use the subsets of the mesh point cloud. So you work in different directions for these two papers, or they are the same in some way.
Yeah, that is a good point. Actually, I also think about this problem, this question during the development of Transolver-3. I think the answer is, like in Transolver++, we are basically want to input the entire mesh into GPU. We do not want to do any approximation for the calculation of Transolver. So all the designs in Transolver++ is aiming at ensure Transolver can process million-scale geometry simultaneously inside one GPU. So that's why we want to use the eidetic slice token. Because if you input the Transolver with a very large mesh, it will cause the degenerated physical states. Well, in Transolver-3, we basically do some approximations, because we do not calculate the physical states based on the equivalent computation by multi-GPU communication. We just do the amortization. We just split the input mesh into several subsets. So in this case, every inference will only receive about, I think it's not million scale geometries. It's just like 30 thousands of match points in each inference. And in such limited match set, you do not need the eidetic slice to ensure a good representation learning for the slides. So that is why we use different directions in Transolver++ and Transolver-3, because we in Transolver-3 actually do not need to handle the large scale geometries, because you're doing the amortization outside the model. It's an approximation, but it works in the extremely large geometries. So if you want to do some applications with large geometries, I think, for example, if you want to handle million scale geometries, I think Transolver++ is still a good choice. But if you want to do more, like you want to scale the geometry into hundreds of million scale, you have to do the amortization. And in this case, you do not need to apply the eidetic slice, just use the original Transolver. That is good. Okay, if that is the answer.
Yeah. So, okay, and my second question is that I also read a paper about your revised the Transolver, and in that paper you propose the linear neural operator that you remove the physical attention part, and it also works, right?
Actually, I think this paper is from the other researchers. I do not join that project, but I think this is a good point. Like, how to say that? I think there are a lot of modifications to Transolver, like there is also a modification like Geo Transolver. They integrate graph neural network into Transolver to enhance the representation learning of each match point. I think that is quite reasonable because in Transolver, we only do the slides based on the pointwise representations. This seems simple, but maybe not very reliable in very sparse spaces. So when talking about the modification of Transolver, I think it works and it's possible to upgrade this architecture. And so why remove attention works? I think we need more investigation. But my point is that what we need to do is to get close to the mainstream architectures. That is a vanilla transformer. So that is my mindset because I'm from the machine learning community. I will do my best to get close to a scalable architecture. So that's my that is my mindset in designing Transolver. So we maintain the original transformer architecture as much as possible in this architecture. And I believe this is more scalable if you scaling the data and scaling the parameters. So that is my answer to the question. So I think they are very interesting explorations, maybe the right way. But in my mindset, I prefer the original Transolver architecture because it's very close to the vanilla transformer. Yeah.
Oh, yeah. You're right. Thank you so much.
Thank you.
Thank you, Wei. Jay, you want to go next?
Yeah, thanks for the presentation, Haixu. It was great. And I think I just wanted to, I had questions about the slicing mechanism. So how is the slice decided exactly? Is it using learnable parameters?
Yeah, this is the hard to understand part in Transolver because like this is you can just view the slice operation as a pointwise classification layer. Like in this way, let's say you have m potential physical states. M is a hyperparameter. You can just set that as 32. And you can use this classification layer to project each match point into m potential categories. And in this way, this is the first step, like pointwise classification. And the next is to the global average pooling, but it's a weighted sum, not average pooling. A global weighted sum for each token. Like you do the spatially aggregation for different match points, then you can get different tokens. But I think this is the design. So maybe I think you are curious about why this design works. I'm also think about this and do some explanation in Transolver's paper. I think it works because it has two reasons. The first reason is if you think about this problem from a backward view, like if you want to reduce the final loss function, the optimization process will driven the learning of the linear classification layers to learn some informative things. Like if you just learn a random classification, the tokenization process is like an average pooling. So the whole attention will generate to an average pooling. You cannot decrease the final loss. So this is the first understanding. And the second understanding, I think, is from the architectural design. We are basically doing the softmax. Actually, softmax is a very interesting function in attention mechanism. And if you are familiar with some ML system to speeding up the attention calculation, you will find that softmax is a very important component because it basically makes the distribution from a uniform to a picky one. So in this way, it will enforce the model to learn some very confirmed this classification for each match points. It's like if you because we are using softmax, it's less possible to learn a uniform distribution. So this will make the model easier to learn some informative tokens. So I think that is two explanation for the slice operation. Yeah.
I see. Thank you. Then my second question would be, for the Transolver-3, you said you're sampling subsets of the original mesh points. Was there any heuristics, or is it all uniform random selection in this case?
Yeah, in this paper, we only do the uniform random sampling. And I think because if you want to do the amortization training, and during the later stage of the training process, the amortization is approximation to it's also an approximation about the entire mesh forward, because you can prove that because during because the learning rate is very small and the parameter optimization is very close to the convergence, so you can prove that amortization training is basically equivalent to the entire meshing forward. Yeah.
I see. Thank you for the answer.
Okay, thank you.
Thank you, Jay. We'll take a last question from Bam.
Yeah, hello. Nice talk. Thank you very much. I'm wondering, like, what is the training data size that required for Transolver can handle, like, I mean, I'm really focusing on the scarce data, like 50 designs or 100 or 150. But from my understanding, this neural network method required larger data sum designs. Yeah, how this Transolver handles data scarce situation.
You mean what kind of physics underlying this data set you are talking about?
I know, I mean, where you can extract training data designs. I would say, like, if you're having simulations, if you're feeding 100 simulation data as an input. Yeah. So
in general, I think Transolver is not a very data hungry architecture. I mean, obviously you can train the model with larger data set and you can get a better performance. But it's also possible to only train Transolver with limited data sets, like in Transolver 3, we train the NASA CRM dataset only contains about 150 samples. So I think it's not very data hungry, but it depends. From the ML view, I think basically if you want to learn a neural network, you are trying to fit a manifold, right? And if you want to cover a very diverse manifold, like you are trying to do the physics foundation model, the data manifold is quite diverse. The data space is quite large. You need more data to fit to fill the whole data manifold. So in that context, you need a large you need data as many as possible. And if you are doing something like physics simulation, maybe you are designing a car or designing an airplane, and in this way, the physics field is quite similar to each other. So in this way, you do not need a very rich training data. I think that is the answer for general usage of Transolver. And during the experiments, I also find some drawbacks of Transolver. Actually, it's drawbacks for all types of neural operators. I think currently most of the benchmarks are CFT based. They want to simulate the fluid. And the dynamics is quite, if you're looking at the physics field here, you will find that the whole physics field is very continuous in different spatial positions. So in this task, I think deep learning will work very well because they can approximate the manifold very accurately and produce a smooth result. Well, if you, I also try Transolver and other neural operators in some structural analysis tasks, like modeling the inside stress and the earthquake of a building. And I find that all the neural networks fails in modeling this task. And their relative L2 will converge to about 20%. I think this is not a good result. And so I think maybe physics, if you incorporate physics laws like pin laws into the subclasses can be helpful. So I think that is the general answer about the transovers usage. If you have a very specific scenario, we can discuss that.
Yeah, because right now I'm doing PCA-based dimensional reduction, then fitting a regression model for each component that I'm getting. So, and that result is better than, let's say, DeepNet or point DeepNet, the current existing operator methods, but I haven't tried Transolver yet. I'm reading the code and trying to understand it. Yeah.
Okay.
But yeah, this PCA-based traditional method is working and neural network method is not working, maybe from my problem. So I'm wondering what is the case with the Transolver. Yeah, just curious before trying.
Yeah. I think this is a very interesting phenomenon, but I'm not quite familiar with physics application. So maybe in general, I think is if you want to pursue a scalable, if you want to pursue a generalizable model, you need to just use physics data. And if you want to solve a very certain scenario, like the application you want to do, you need to integrate the physics laws, like pin laws, because that is necessary. Yeah.
Yeah. Okay. Thank you.
Thank you.
Thank you, Bam, and thank you, Haixu. Actually, the last point that you made is very valid. We also feel the same thing. Most of the benchmarks are in fluid mechanics, and there's very less of such data sets available in solid mechanics.
Yes.
I'm not sure if you know that my group is also producing a couple of data sets on fracture. So,
okay.
Yeah, we are trying to do it. Of course, we are not there as of now, but we are trying to build some data sets which can be applicable for solid mechanics.
Okay, I think that is very, very helpful, and we should build our architecture oriented to that data set, because it's kind of I have to say it's kind of easy to solve CFD. I don't mean easy in physics learning, but it's easy in fitting the data manifold of CFD.
Yeah, true. The other question, I actually wanted to ask you something regarding the Transolver. So I did try Transolver, but that was your first version. And what I saw over there is that I was unable to capture the fine scale details for the Naka airfoil I was trying. So I was wondering, have you thought something on the direction of like multi-grid or some kind of activities where we can take into account the multi-scale features and make it multi-scale?
Yeah, I think that is a great point. And basically in Transolver, in Transolver's paper, we do some visualization and find that maybe the Transolver architecture in the inherent multi-scale, like in the beginning layers, they will capture some fine-grained information. In the upper layers, they will capture some more abstract representations. So I think this architecture can actually capture the multi-scale information. That is why current vision transformers just use VIT, just is a pure transformer, why they can capture the multi-scale patterns in images. And I think it's important to pay attention to the fine-grained details, because that is definitely I cannot do, and you are Professor Yu and your team are the expert in the mechanical engineering, and you will find some drawbacks in current deep learning architectures, and identify why they cannot produce the fine-grained details. And in Transolver, I think if you think about the physics attention from a very shallow view, like why we can reduce the computation complexity. This is because we are doing something like sparse learning. We are make the correlation modeling into a sparse version. It definitely removes some valuable correlations. but it's a trade-off between efficiency and performance. So I think I think it's very important if you have a multi-scale architecture, like you can capture the fine-grained details in the lower scale, and I mean in the fine-grained scale, and learn more reduced interaction in the higher scale. And I think that is very promising. Yeah.
Great. Yeah. If we go around doing something, I'll definitely reach out to you again.
Thank you. Thank you.
Yeah, thank you so much. I think that would be it. We are already over time. Thank you for the wonderful talk, Haixu, and for logging in today.
Thank you.
And to all our other audience, thank you so much for tuning in today. And we look forward to again seeing you next week. Thank you so much.
Thank you.
Thank you, Haixu.
See you. Bye-bye.
Bye.